Greetings. Welcome to today's class. So let us get started with today's class. So if we recall in the previous class, we were looking at just a brief recap of mechanics, and then we started off with what was meant by a frame of reference, an initial frame of reference, and then we defined center of mass, center of gravity when they are the same. And we essentially came to the Newton's second law of motion, right? So because we are essentially going to consider what is called Newtonian mechanics. And I left you with a question, right? So we saw that Newton's second law of motion is essentially that the net force acting on the body is proportional to the time rate of change of linear momentum. But the mathematical form of Newton's second law of motion that we are typically familiar with and most commonly utilized is that F equals mv. Right? However, we realize that one of the assumptions behind using F equals mv is that the mass should be constant. That is point number one. And even if the mass were constant, right? So we saw that F is only proportional to ma, right? So the question becomes when is it equal to ma? So I left you with that question, as to when the proportionality constant becomes equal to 1. So could you look at it? Any thoughts on when the proportionality constant is 1?
So it is due to experiment that 1 kg of mass accelerated to a 1 meter per second square with a 1 Newton of force.
Okay, so you are almost there. So actually the constant of proportionality depends on the systems of dimensions and units chosen, okay? So that it is essentially related to that. If you choose the SI system of units where 1 Newton is defined as the force required to accelerate 1 kilogram of mass at 1 meter per second square acceleration, then using that system of unit and these definitions of the quantities involved, the constant of proportionality becomes 1. Okay, so the answer to this question is that the value of k, right? So let me write what that is. Okay, so the value of k, proportionality constant, right, depends on the system of dimensions and units. So that is the answer to this question. Okay. So consequently, if we use the SI system of units, K becomes equal to 1. And this implies that F becomes equal to M times A. Okay, but this is not the case always. There are units such as what is called as the for example, the United States customary system of units, where which is called as USCS, okay, where K is not equal to. Okay, so I will let you figure out, what this unit system is and what is the value of K in that system of units, as an exercise, but please do look it up, it's very interesting. And then we all of us will understand why this is one of the reasons why we have also moved to this SI system of units, right? So not only do we want to be consistent in our quantification of various variables and parameters, but we also ensure that these equations are going to be in the simpler form, when we are essentially choosing the SI system, particularly Newton's second law of motion, which is very important for vehicle dynamics. Okay, so that's something which we need to. So this F equals ma becomes the primary governing equation to capture what is called as translational motion, okay, of a rigid body. Fine. So now I'm just going to take you on an aside, okay, just as a side note. So what is this side note that I want to share with you? Let us say, like we even take 1D motion. Okay, so let's not worry about vector quantities. We essentially consider all the quantities to be scalar just for simplicity. Okay, so as our friend correctly told, like we take the unit of force in the SI systems as newtons, and the unit of m mass is kilogram, and the unit of acceleration is meter per second square. Correct. So 1 Newton of force accelerates 1 kilogram of mass at 1 meter per second square. So that is the equivalence. Now, in vehicle dynamics, like typically, if we look at acceleration, it is typically specified in G units. So what is G units? So we essentially say example, like acceleration or deceleration. Like let's say acceleration is 0.2 g, deceleration is 0.5 g, and so on, right? So what is this 0.2 g? That means that we are essentially normalizing the acceleration by the acceleration due to gravity and reporting. Okay, so this implies that acceleration normalized with respect to the acceleration due to gravity is 0.2. Okay, so this is something which is important. Okay, so we need to remember this, right? Because this is a very common convention used in vehicle dynamics. So when we say acceleration is in term of G units, we need to convert to meter per second squared before we apply it in the uh, governing equation. Okay, that is point one. Second point, which I also want to just share with you, is that see, even when we talk about various parameters associated with road vehicles, right? Let's say one of the parameters being the gross vehicle weight. So although the expansion is gross vehicle weight, the unit is of that of mass. Okay, so this is sort of something which we need to be aware of. So people will say, oh, gross vehicle weight of the car is, let's say, 1.5 ton. That means 1,500 kilograms, right? So we can see that although the term is having the word weight in it, the unit is that of mass. Okay, so that is something which we need to remember. All right. And one interesting point related, yes, please.
Sir, actually, your voice is breaking. I don't know whether it is for only for me or.
How about others? Is it okay? No.
Yeah, it is okay, sir.
Yes, sir.
Okay.
It is okay. Fine.
It's okay for me, sir. It's good.
All right. Okay. So, what I will do is that, as usual, I will share the video file also after the class. So, in case if there is any network perturbation at either end, please do watch the videos. And if there is any issue with the video or some part of it, I can please point it out to me. I will repeat those portions in the next class also. Okay. So we will. As I was saying, right, so the unit of mass is kilogram, but in vehicle dynamics, when we specify vehicles, we talk about the gross vehicle weight. Although the word weight comes there, the unit is that of mass. Okay, so we should remember that. And in fact, interestingly, we can rewrite this equation in this form. Okay, so let's say we have F equals ma. We can essentially write it as mg times a by g, right? We can always do that. This mg is essentially the weight of the body. Okay, so we can even write this as w times a by g. Okay, so this is also an equivalent way of writing this expression that we will encounter while we write the governing equations of motion in vehicle dynamics. Okay, so but then please note that w is now weight. Okay, vehicle weight, and that unit is that of the unit of it, that quantity in SI units is Newton. Okay, so we need to remember that. So we have to be very careful when we substitute, appropriate quantities and governing equations while solving problems. Okay, so I just wanted to point out these facts. Okay, before going ahead. Okay. So let's go ahead. Are there any questions regarding what we just discussed? Like to summarize, if we look at Newton's second law of motion for translational motion, the governing equation becomes F equals ma under two assumptions. The first one is that like the mass of the object is constant. The second assumption is that like we are using a system of unit such as the SI system where the constant of proportionality is 1. So as an interesting exercise, please find out in which other systems of units the constant of proportionality is 1 and which systems of units the constant of proportionality is not equal to 1. Okay, I gave you one system of unit, the USCS, right, where the United States customary system of units where the constant of proportionality is not 1. In that case, please find out what is the constant of proportionality. And please also find out other system of units if they exist where the constant of proportionality is 1 and also not equal to 1. Okay, please do that as an exercise. In this course, we are going to use SI units. So we are fine, like we can just use F equals ma, assuming that the mass of the vehicle is constant. Okay, so I hope that clarifies these important points. Okay, so now moving ahead, it's not necessary that like a vehicle needs or a rigid body needs to undergo only translational motion, right, along one direction. So we can also have rotational motion about different axes. So what happens when we have rotational motion? So for rotational motion with respect to an inertial frame of reference, so see, where do these equations become important? Suppose, let's say we want to study the pitch motion or the roll motion or the yaw motion of a vehicle, right? So then these governing equations become very important. So when we have rotational motion and we write down the equations with respect to an inertial frame of reference, so what happens is the following. Okay, the time rate of change of angular momentum, which is now I naught times omega naught. I will explain what these are. That's going to be equal to tau naught. Okay, so let me explain what these quantities. So here, tau naught, which comes on the right hand side, is the torque which is applied on the body. Okay, so that, for example, if we essentially consider yaw motion, right? So there can be a torque which comes on the body due to the longitudinal forces and the lateral forces applied on the vehicle at the tire road interface, right? So, and we could also have like other effects creating a torque about the yaw axis, right? So that is always possible. Okay. Now, what is this omega naught? Omega naught is the angular speed vector. Okay. So, and what does this subscript naught indicate? The subscript naught indicates that all the parameters are returned with respect to an inertial frame of reference. Okay. So we'll shortly see what happens when we write these parameters with respect to a non-inertial frame of reference. Okay. Omega naught is this. Okay. And what is this I naught? I naught is the moment of inertia tensor. Okay, so this is nothing but this is a matrix. Okay, so it's called as a moment of inertia tensor or a matrix. Okay,
Sir.
So yes, please.
Sir, this is I alpha, right, sir? Which is angular acceleration.
Yeah. So please note that I have written the time derivative outside. Okay, when I naught is constant, it becomes I alpha. Okay. So, exactly. Okay, that's a good observation. I think you have preemptively observed what I was about to tell. That's good. So typically, if you remember, even in 1D, when we write equation of motion for rotational motion, we write I alpha equals torque. What is alpha? Alpha is the time rate of change of omega, right? Of course, I'm writing in one-dimensional motion. So please note that here I have not written I naught alpha, right? So so essentially, I have written the time rate of change of angular momentum. So please note that I omega is angular momentum. Okay, so when do we get I alpha? When I is constant. So similar story, right? So when the moment of inertia is constant, this left-hand side of the equation which I have written down becomes I alpha. I hope that is clear, right? So, but this is a general equation, all right? So it is always better to start from the general equation, and if the moment of inertia is a constant, well and good, we can write I alpha, otherwise we need to be careful, right? So that is the point, right? So I hope that clarifies. That's a good observation. Okay. So now what happens when we have, when we want to write the equation of motion for rotational motion with respect to a non-inertial frame of reference, like so, see, for example, let us say many times we are going to do that, like particularly even the next module when we deal with lateral dynamics, we are essentially going to deal with a motion, like when we are going to have a frame of reference, let's say fixed to the vehicle's center of mass, right? So, and then like we are going to consider the yaw motion by writing equation with respect to that frame of reference, right? So then it becomes a body fixed frame of reference, right? So that's a non-inertial frame of reference. So when we have, when we want to characterize or write down the governing equation for rotational motion, with respect to a non-inertial frame of reference, such as a body fixed frame of reference. So what happens, okay, to the same equation? So let me write down how this equation changes. What happens is the following, okay, we get the moment of inertia times omega dot, okay. So omega dot is alpha. So this now, let me be very careful. Let me put this dot only above omega, okay, plus omega cross I omega, all right, that is equal to tau. So we can see that there is an additional term which comes on the left hand side of this equation, okay, and this term, I'm sure all of us would have heard about this term, is what is called as a gyroscopic term. So see, what I'm doing is that like I'm just writing all the equations in 3D, okay, so for general motion, so that like we can always derive specific cases from general equations of motion, okay. So that is the, so this is the important governing equation for rotational motion that we will be using whenever we are going to write equation with respect to non-inertial frame of reference. When we write equations for rotational motion with respect to an inertial frame of reference, we will be using the one that I wrote down above, okay, this particular equation. So you can clearly observe that there is a slight change in the notation, and when we essentially write down the equation of motion with respect to an non-inertial frame of reference, such as a body fixed frame of reference, we get this gyroscopic term appearing in this equation. Okay, so that's something which is very important. Okay. So, and this formulation, that is using F equals ma, and this equation, what we wrote down for this set of equations, right? That we have written down for rotational motion, they constitute what is called the Newton-Euler formulation. So Newton-Euler formulation includes as F equals ma, d by dt, I naught omega naught equals tau naught, and then I omega dot plus omega cross I omega equal to tau, right? So all these constitute what is called as a Newton-Euler formulation, which is one way of essentially writing down the governing equations of motion when we consider rigid body mechanics. Okay, so in the Newton-Euler formulation, what we do is that like we consider the forces and torques acting on the body, and we relate them to the various kinematical quantities such as accelerations and velocities. Okay, so that's what we do in Newton-Euler formulation. All right. So now let me also present what is called as the Euler-Lagrange formulation. Okay, so which is an alternative. So once we learn this, we will do an example also. Obviously, like when we are given a mechanical system for which we need to write the dynamic governing equations of motion, we will get the same answer irrespective of whether we use the Newton-Euler formulation or the Euler-Lagrange formulation. Okay. So, but then these are two different methods to write down the governing equation of motion. Of course, one may ask the question, hey, when do we use what, right? So once again, the answer is not very straightforward, like we get an intuitive feel of when to use which method at experience. Okay, so but then the bottom line is that like when we use either method, we should get the same equation of motion. Okay, that because the system is the same. All right, so that is good. Okay, so what do we do in Euler-Lagrange? Okay, so in Euler-Lagrange formulation, we define what are called as generalized coordinates for the body or the system of bodies under steam. Okay, the rigid bodies under steam. So let us consider Q1 through Qn. Okay, when we do the example, it will become clear what these are. Okay, so we define right now. Let me present the general framework, and then like we will essentially learn how this is helpful, right? So, and then how do we choose these variables and so on. Okay, so these are what are called as generalized coordinates. Okay, and then we define a vector of generalized coordinates Q, which is a column vector where we arrange all these n generalized coordinates. Okay, Q1 through Qn. Okay, so let us say, like we have an n degree of freedom system, like we define n generalized coordinates, Q1 through Qn, and we form what is called as the generalized coordinate vector. Okay? Then we define a quantity called as the Lagrangian. So this Euler-Lagrange method is, like is visualized as a method that uses an energy-based formulation. Why do I call it that way? That is because of the definition, the way the Lagrangian is defined. Okay, so what we do is that like it is the difference between the net kinetic energy so let's say we have the system, we have different rigid bodies, and then like we evaluate the kinetic energy of each rigid body, right, an element. Okay, we'll see what those elements are shortly, and the net potential energy. Okay, so net potential energy U of the system components. Okay, so the way we are defining the term Lagrangian is this. That is, the Lagrangian associated with the system is the difference between the net kinetic energy capital T and the net potential energy capital U of the system constituents. Okay, so what we have is that like L is essentially going to be T minus U. And it so turns out that the Lagrangian L will be a function of the generalized coordinates and its derivative. Okay, the generalized coordinate vector and its derivative. Okay, so you have Lagrangian being a function of Q1 through Qn and Q1 dot through Qn dot. Okay, the Q1 dot will come because of the kinetic energy terms. We will shortly see how these come into picture. All right. So that's the Lagrangian, and then we also have what are called as generalized forces. Okay, so once again, please bear with me. These things will become very clear when we do an example. So we also define what are called generalized forces. These include both forces and moments. Okay, like as far as the Euler-Lagrange method is concerned, and we essentially call this generalized force vector as tau. Okay, so please. What to say? Do not think that since we have written tau, this will be a vector of torques. Okay, not necessarily, although this is a symbol which is typically used. This vector tau is essentially a combination of forces and torques. Okay, so that should be kept in mind, right? So having set up all these things, the Lagrange's equation of motion, okay, when there is no dissipation. Okay, so let me write down the first case. Okay, so the Lagrange's equation of motion, okay, without any dissipative effects. Okay, so what do I mean by dissipation? Without dissipation, let's say there is no friction and other effects, like which lead to loss of energy, right? So when we don't have any dissipative elements in the system, so I'm not deriving it, I'm only sharing the final result. It is given by d by dt of L del Q dot. Okay, so essentially we take the partial derivative of L with respect to Q. Let me write it very carefully. Okay. Del L del Q dot. Okay, so we take the partial derivative of the Lagrangian with respect to the Q dot vector, and then we take the time derivative of the resultant vector. Okay, so that's what we do. Minus the partial derivative of the Lagrangian with respect to the generalized coordinate vector q, and this is equal to tau. Okay, so this is the equation of motion, the Lagrange's equation when we don't have any dissipation in the system. Okay, no energy dissipation in the system, and the system constituents. Okay, so that is the Lagrange's equation. Okay, of course, one may ask, hey, how do we get all these things? Okay, so in order to clarify that, let's do a simple example. Okay, so let us consider the 1 degree of freedom mass spring damper system. Okay, so I am not going to consider damping right now. Okay, so we will see what impact damping will have on the system response shortly. So right now, what I'm going to do is that, like, I'm going to consider a very simple system where we have this mass m. Okay, and then we only have a spring constant k, and a force is applied on this mass, which is f of t, and the displacement of the displacement of the mass from its equilibrium state is x of t. Okay, so that's what. All right. So let's assume a frictionless surface. So for the time being, so there is no energy dissipation in the system, right? So we already know what is the governing equation of motion, right? So let me write down the answer. Okay, so but then, like, we will essentially get the answer by using the two correlations, right? So we already know that this is a system for which the force is the input and the displacement is the output, right? So that's something which we already know. So now what we are going to do is that, like, we are going to get the governing equations using the two formulas. So first, let's try out the Newton-Euler formulation. Okay, so if we try out the Newton-Euler formulation, what happens? We essentially draw the free body diagram and then we write F equals ma. That's what we are going to do, right? So because this is a 1 degree of freedom system and we are only having translational motion, so essentially what we have to do is that, like, the force acting on the body in this direction of motion, the applied force is F of t. Okay, and the restoring force due to the spring is going to be k times x of t. Okay, so these are the two forces. So consequently, what happens? Ma equals F. So m times a, which is x double dot, is going to be the net force acting on the body, which is going to be F of t minus the restoring force due to the spring, which is going to be k times x of t, right? So this is the equation of motion by using F equals ma, right? So that's all we have done. So rewriting this equation, we get the answer, right? Very, very simple. So this is something which all of us are already aware of. I'm just repeating it. So we get the equation of motion as mx double dot plus kx equal to f of t, right? So we are aware of this equation of motion. Okay. So now, having looked at Newton-Euler formulation, let's look at the Euler-Lagrange formulation. Okay. So let me complete this exercise, then we can also discuss any questions. Okay. So we have Euler-Lagrange equation. So we can see that here, this is a 1 degree of freedom system, right? So we essentially need to choose only one generalized coordinate. Okay. So let's say we choose q and t to be the displacement x of. Okay, so which is the degree of freedom of the system, right? So let us choose that to be q, right? So there is only one essentially degree of freedom. So what I'm going to do is that I'm going to drop this subscript 1, and it is understood that we are dealing with a scalar variable, right? So I'm not putting a tilde underneath q. So q is only one variable, right? So it's a scalar value variable, right? Okay. So consequently, if we take the time derivative of q, it is going to be x dot, right? Which is going to be the speed of the ball mass, right? So that's something which is very obvious. Now, let's form the Lagrangian. So the Lagrangian, as we know, is going to be T minus U. So what is T? T is the kinetic energy, right, of the system constituents. Here, when the kinetic energy will be associated only with the mass, right? So what is the kinetic energy of the mass? It is half mv squared, right? So essentially, I'm going to get the kinetic energy as half m times x dot square, right? So I'm sure that is very obvious, right? And as far as potential energy is concerned, anyway, we are not going to have any potential energy term associated with gravity effects due to the mass because we are moving in the horizontal direction. So the only potential energy term is due to the potential energy stored in the spring due to its displacement, which we know is going to be 1/2 kx squared, right? So I'm sure all of us can um, relate to this, right? So I hope this is clear, right? So how we got these two terms. Okay. So yeah, any questions on how we got the expressions for T and U, which are the kinetic energy and the potential energy? Okay.
Sir,
Yeah, any questions?
potential energy, how did you got of kx square?
So essentially we have a spring, right? So due to this deflection of the spring, there is a potential energy term which is stored in the spring, okay? And one can derive that as 1/2 kx squared, all right?
Okay, sir.
Okay, so yeah. So, so essentially, it is like this, right? So, if you see, if in fact the energy, essentially, we need to integrate the product of force and displacement over the displacement of the body, right? So, essentially, if we have kx as the instantaneous force, and let's say dx as the infinitesimal displacement of the spring, right? Kx times dx will be the what to say, the instantaneous work done, and then like we integrate it over the range of displacements, like assuming that k is constant. Of course, this is an important assumption, right? Yeah, good that you brought it up. Okay, assuming that k is constant, this is an important assumption. Okay, so we assume that the spring constant is indeed a constant value. We get 1/2 kx. All right, so okay, integral x dx is x squared by 2, right? So I hope it's clear, right?
Yes, sir.
Okay. Okay. Fine. Any other questions before we go ahead? Okay. So now let's evaluate each term in that expression, the Euler-Lagrange equation, right? So the first term is going to be d by dt of del L by del Q dot. Of course, here we only have a scalar variable, so I'm just going to put Q dot, okay, as a scalar variable. Okay. So let's evaluate this. It is going to be d by dt of what is del L by del Q dot? I need to essentially take the partial derivative of the Lagrangian with respect to x dot. So this is going to be del by del x because Q dot is x dot of by 2 mx dot square minus 1 by 2 kx square. Now, when we take the partial derivative, this is going to give me 1 by 2 times m times 2x dot. Okay, that will be the partial derivative of mx dot squared with respect to x dot, right? So when I take the partial derivative of x dot squared with respect to x dot, I get 2x dot, right? And then when I take the partial derivative for the second term, 1/2 kx squared, there is no x dot term coming there, right? So that is 0. Okay. So consequently, the partial derivative of the Lagrangian with respect to q dot will just be m times x dot. Okay. So I hope it is clear how we got m times x dot. All right. So once again, let me repeat. So q dot is x dot. So we want to take the partial derivative of the Lagrangian with respect to x dot. And then the first term, the kinetic energy term, is 1 by 2 mx dot square. So when you take the partial derivative with respect to x dot, I get 2x dot, right? Because m is constant. So essentially, I get 1 by 2 m times 2x dot. All right. For the second term, which is the potential energy of the spring, that contains only term involving x. But then I am interested in partial derivative with respect to x dot. So that partial derivative of 1 by 2 kx squared with respect to x dot becomes 0. Okay, so that's why I get the answer as mx dot. Now we need to take the time derivative of mx dot. So what is the time derivative of mx dot? This becomes mx double dot. Okay, so of course I'm suppressing parenthesis t in some places. Sorry about that, but I am sure it is understood which variables are functions of time and which parameters are constant, right? So yeah, all right. So m is constant, so we get mx double dot. Okay, so that is how we get the first term. Now let's go and look at the second term. So when I want to calculate del L del Q, I want to essentially take the partial derivative with respect to x of the Lagrangian. So this will be del L del x of 1 by 2 mx dot square minus 1 by 2 kx square. So what do you think will be the answer? Can you help me with this now?
Only kx.
It will be only kx, but with the negative sign. So we should not forget the negative sign, right? So good. Okay. So you can see that the first term, the partial derivative with respect to x is 0. Okay. So the partial derivative of 1 by 2 mx dot square to x is 0. But the partial minus 1 by 2 kx squared minus kx, right? So we get the partial derivative of x squared with respect to x will be 2x. So the half and the 2 will get cancelled. So we get minus kx, right? So I hope it is clear how we go. So now we essentially to use this equation, right? So we are going to write down this equation, right? So then the governing becomes thus the governing equation is. So what is the generalized force? The generalized force is nothing but the force applied. Okay. So I should also write that tau of t in this particular case is only the force which is applied on the body, right? On the mass, F of t. Okay. So the governing equation is d by dt of del q del dot, which is going to be mx double dot t. Okay. The term on the left hand side minus, there is a minus in the governing, right? And then del x, which is going to be minus kx, right? And be equal to the generalized, which is f of. Okay. So what do we get from here? We get mx double dot plus minus of minus, we get kxt is equal to. Okay. So we can observe that we get the same answer, right? As with the Newton-Euler formula. All right. So I hope this derivation is clear to everyone, right? So how we are able to apply the Euler-Lagrange formulation. Okay. Obviously, we should get the same answer, right? So otherwise, we are not doing something correct. Okay. Any questions before we go to Lagrange's equation with dissipation? All right. Okay. So I am going to essentially now write down the Lagrange's equation with dissipation, and then I will give you an exercise problem. okay, to essentially learn how we can use this. So of course, see the previous problem, we didn't consider any dissipative effects, right? So for example, we didn't consider any damping, friction, and so on, right? So, but however, let's say we consider damping forces and so on, right? So viscous damping forces, like what we get in the damper, right? The viscous damper. So what happens? So we consider those scenarios where the dissipative forces are proportional to the velocity. Okay, so this is a presumption that we use, but this is a very useful presumption to apply this Euler-Lagrange formulation under such cases. Okay, so let's consider the scenario where the dissipative forces are proportional to the body's velocity. Okay, so that's the scenario we consider. Okay, so now we introduce what is called as the Rayleigh's dissipative function. Okay, so the Rayleigh's dissipative function, okay, models, which is denoted by df, is used to model the dissipative effects. Okay, is used to characterize the dissipative effects. So this is a function of this is also like an energy term. Okay, it's a dissipation function, not a dissipative function. Sorry about this. This is what is called Rayleigh's dissipation function, is used to characterize the dissipative effects. Okay, so this is like energy lost due to such dissipative terms or dissipative elements which come in the system, like a damp. Okay, so then once we include the Rayleigh's dissipative function to model these dissipative effects, the Lagrange's equation of motion becomes, okay, the Lagrange's equation of motion in this case becomes the following. So what this is, this becomes d by dt, sorry, d by dt of del L del Q dot. Okay, the first term remains the same. Sorry. Okay, minus del L del Q dot. This sorry del Q. Sorry, this term also remains the same. However, there is a third term which comes on the left hand side, which is del df del Q dot, partial derivative of the Rayleigh's dissipation function df with respect to Q dot. Okay, typically the Rayleigh's dissipation function is a function of Q dot, and we essentially take the partial derivative of the dissipation function with respect to Q dot, and this is going to be equal to the generalized force vector tau. Okay, so this is the modified equation of motion. Okay, in this particular case, we have the dissipation function. All right, okay. So now, essentially, let us consider the mass spring damper system. So this is the first problem I'm going to give you in homework number 4. Okay, so consider the mass spring damper system. Okay, so consider mass 1 degree of freedom, right? So 1 degree of freedom, mass spring damper system. So let me draw the standard diagram that all of us are familiar with, like as far as this system is concerned. So once again, we have mass m. Okay. Sorry. Mass m. Okay, on which we apply a force f of t, and its displacement is x of t. We have a linear spring whose spring constant is k, and then we have a linear viscous damper whose damping coefficient is C. Okay, so this viscous damper models the dissipative effects. Okay, and the Rayleigh's dissipation function for this viscous damper is going to be dF is going to be equal to 1 by 2 C times x dot square. Okay, so this is also something which I'm giving to you, right? So what is it that I want you to do? Okay, so what I want you to do is that like derive the governing equation of motion. Okay, using both the formulation. So anyway, it's a very simple exercise, but I want you to do it, right? So using the Newton-Euler formulation and the Euler-Lagrange formula. Okay, so please do this as part of homework number 4. Of course, we know the answer, right? So say this is a problem where we already know that the answer should be mx double dot t plus cx dot t plus kxt equals f of t, right? So we can immediately sort of easily do this problem in 2 minutes, right? So we can observe that the only difference between the previous equation of motion that we did earlier in today's class and this equation of motion is the appearance of the term cx dot, right, due to the viscous damper. So, but however, like please do all the steps and follow the processes that we have established for the uh, essentially Newton-Euler formulation and the Euler-Lagrange formulation, and do this problem and get this equation. Fine. Okay. All right. So these are the main concepts that I wanted to share with you today. The basic two main formulations that are used in rigid body dynamics, the Newton-Euler formulation and the Euler-Lagrange formulation. The question is, like when do we use which one, right? So that's a natural question that we get, right? So and the answer is it depends, right? So many times, like many applications in engineering, like the choice of the method also, we become good at choosing the method with experience. So let us say we have a complex system which has multiple components and we are not in a position to essentially write down the equation of motion for each component or each subsystem, right? However, we want to essentially lump all the effects and get the equation of motion. Many times we go for Lagrange's formulation or the Euler-Lagrange formulation, right? Where we identify the generalized coordinates and then like we write down the potential energy and the kinetic energy terms and then like use the Lagrange's equation of motion. But sometimes that may not be possible. So then we go for the Newton-Euler formulation where we try to break down the system into simpler subsystems, components, and then like we draw the free body diagram and balance out the forces and moments. Okay, so both formulations are useful. The important point is that like you take a system, you apply both formulations, obviously you should get the same answer, right? So that is the final check which is useful to us. Okay, so we need to keep that in. All right. So that's two formulation. Those are the two formulations. So we'll stop here, and then like we will continue with our discussions in the next class. Before I close, any questions on what we learned today? All right. So if not, I will stop recording. Thank you.